All right, I'm just letting everybody kind of join here, get connected to audio, and then we'll get started. All righty, welcome everyone. My name is Megan Miller, and I'm one of the graduate program specialists here in the computer science department. Today's uh, sorry. Today's session is going to be full stack data analytics, systems, algorithms, and applications presented by Professor Christine Liu. She's going to do a brief overview and then we will follow up with questions. If you do have any questions during the presentation, feel free to use the chat feature. Otherwise, we can save them for the end. All right, I will hand it over.
All right, great. Thank you, Megan. All right. Hello, everyone. Thank you for joining the session. Let me start my slides. All right, hopefully you're seeing my slides now. So this is actually my full stack of slides, which I use generally as more like an intro of my research. Okay, so it has actually a lot of information and actually quite a bit of some of the details. So I'll use the slides. I'll like skip a lot of the details on quite a few of the slides, but hopefully this will give you a high level overview of the kind of research I do. And as Mika has mentioned, like we'll have some time in the end for Q&A, but if you have questions on specific slides as we go along, you can put in the chat window, okay? All right, so I'm a professor in the computer science department. I have a reasonably long title because I'm trying to like capture the key things I do and use some of the keywords. Because usually when we say like data analytics, right, there are different flavors. Okay, so over the years, I have worked on kind of quite a lot of different problems related to scientific discovery and ubiquitous computing. But also when I say full stack data analytics, that's really this integrated view of systems, algorithms, and applications. Okay, so that's why I have all this on this slide. Okay. So when we start the whole thing, like starting point is really about data, right? So if you're looking at like the what do we call the digital like universe, right? It's really about all kinds of data being generated, but more important about we don't just store the data, right? We want to be able to do something with it, okay? And also when you look at the data, they're so diverse, right? They come very different domains, they have very different kind of like usage scenarios, okay? So for me, like over the years, as I like look at the different problems and I pick a different problem to work on, I have been kind of focused on two related areas. One is broadly in terms of scientific discovery, the other one just people, right? Think about our daily life and the different kinds of data we interact with, okay? When you look at the data, right? So of course you say you will understand what kind of data you are dealing with so that you can like utilize the data for different purposes. Okay. Some of you may have heard this like different V's that we try to kind of characterize different types of data. Okay. So first, of course, it's just about the sheer size of the data, right? So big data has been used as a term, really just highlighting how large the volume is. Okay. But beyond that, right, there are actually a few other ones that are also very important. Okay. Variety basically speaks to just the different types of data, right? They're so different. So you work with them differently. Your methods may be different. Okay. But also the fact about velocities. That means like nowadays, right, we don't just go to the field, collect one batch of data and be done with it, right? Data is continuously being generated. So, and because of that, right, you are dealing with this very dynamic like stream of data coming in. Okay. The fourth one was actually added a little bit later. This is about the veracity. Okay, we really mean this is about the quality of the data. Okay, because generally like there's this notion about like if you have like garbage data coming in, then you will have garbage results coming out, right? So there's a lot to read about how you actually kind of understand, characterize the different types of data, but ultimately about bringing out value. Okay, because what we want is to use the data to do something useful. So that's all a lot of times say when you are trying to work with the data, start with a good understanding of the problem and then say, okay, what can I do with it? Right. And if you say I build a model, I found something, always ask this question about so what, right? How can this be useful? Okay. So over the years, I have been, of course, focused on data, but the many different aspects kind of evolved over time. Okay. So my earlier research focused more on the kind of the management side. So that's about like when you have a lot of storage space, how you store them, how you find the information, right? But at this point, it's more about just the blocks of data, right? But later on, it's really about, okay, you want to be able to explore the data, bring value out of it. Okay. But to do that, right, you're basically asking these two related aspects, right? One is about efficiency. That's about how efficiently can you handle your data? How efficiently can you build a model? How efficiently can you make a decision? Okay. The effectiveness is also about like how good, right, your model is, how good your results are. Okay. To do that, right, my background is more on the system side. So we actually look a lot about the system design angle. But quickly I realized that, okay, it's not just systems, right? You need the algorithms combined with the system in order to address different types of problems. And then application-wise, that's when I say scientific discovery, ubiquitous computing. So those are really like some areas that are driving a lot of my research work. Okay. One thing to highlight is about this like interdisciplinary aspect. Okay. Data comes from different domains, right? You don't just say, give me the data, I do the work, I give you back a model or results, right? You actually work closely with domain experts. Okay. And that is also like a very important aspect I always emphasize like when I recruit new students. Okay, so full stack data analytics, what do I mean, right? So I'm using two quick examples, okay? First one, this is when we started working with like power electronics, okay? This is about plug-in hybrid electric vehicles, okay? So the starting point is, okay, we want to understand how the vehicles are performing, how the battery systems are working, so that we can like see whether the system can be designed better, right? So from my side, I'm not expert in terms of power electronics, but like I was interested in data, right? So we started saying, okay, what kind of data can we gather about the vehicles and how the vehicles are being performing? So we actually developed some system to the monitor, right, the driving behavior, because how you drive your car and what kind of conditions you're driving your vehicle in, and also how the vehicle is performing, right? So all this come together. When you have the data, this is the part that took me quite some time to learn. Okay, this is where I say, okay, I need to learn from the experts about the different modes of operation. Okay, so from the data side, it's about some kind of classification problem, right? You want to be able to classify your vehicle like operation, right, under the different scenarios, and ultimately we are then able to model, right, the fuel consumption and the CO2 emission. Okay. Also, we actually were able to predict the battery system capacity like 15 years down the road. Okay. What we're seeing from this analysis is really just, okay, how people drive their vehicles, right, can really impact the performance of the vehicles. Okay. And later on, we did this like a nationwide study. This is really just looking at how people like charge their vehicles, how they drive it. And like this actually motivate like a later research that I'm going to talk at the end of the work that is actually ongoing and has motivated a big center-wide effort. So as you can see, right, this is where you have systems. You need to build the system to get the data. You need to manage the data. But the algorithm side is a lot about like classification, modeling, prediction. Okay, but it's tied closely to a example, this is about people, okay, group event scheduling. Okay, so some of you may have had this like experience of say for group you want to go out do something, right? So you want to say, okay, let's find a time or location or figure out where what do we do, right? So we build this app to understand how groups make decisions. Okay, so we have this quite a bit effort building this app, and then we collect data about different groups, right? Suggesting venues, location, time, and then how the group make decisions. This then motivated us to design an event venue recommendation system. This is for a group of people, okay? So there are some mechanisms in terms of how you actually understand the individual preferences, but more importantly, how the group, right, as a whole, make a decision, right? Because you cannot just take the, say, 5 group members and do an average and get the vote, right? So there are different group dynamics and people have different preferences, and the weighting or the consensus function may be quite different depending on the group social dynamics. Okay, so those are two motivating examples. Okay, so this is a slide that has a lot of content, but it really intends to give you a big overview of what I do. If you have a look at my website, you may have seen this. Okay, so I'm talking about full stack data analytics, systems, algorithm, applications. Okay, so systems layer is a lot about how you get the data, right? So this is a lot about the sensing. Okay, so we have worked with mobile, wearable, IoT devices, really just kind of sensing in very different scenarios. Okay, so air quality, driving, earthquake, running, whatever. So there are actually quite a few, right? But a lot of that focus on building the system, but like collecting the data and actually analyzing data for particular purposes. Okay. In the middle layer, there's a lot about how you manage your data, how you analyze your data. Okay, so some of the research focus, like our group have been doing, is about one, fusion, right? We mentioned earlier, like the second V, right, which is the variety, right? You have very different types of data, and they cover very different spatial temporal granularities, right? How do you fuse them together, and how you actually analyze this kind of spatial temporal data, right? To be able to make predictions, to find anomalies, and also make recommendations. So there's a lot of this algorithmic design, but always focus on what kind of data you have or what kind of problems you're trying to address. Okay. At the application layer, of course, there's a lot. That's why it's exciting, right? I have worked with many domain experts, okay? Usually there are some very interesting problems, right? Data related, but challenging, okay? So a lot of time it's just about like we coming from different aspects, right? Working together closely, okay? Understand the problem, come up with solution to see how it works and the different problem setting, okay? The other side, as I said, ubiquitous computing, a lot is about people, right? So we try to understand the user activities, the group behavior, some of the event, cyber safety I also mentioned later. We also do quite a bit with online social networks, okay? So when I originally started, right, this projects, right, scientific discovery seems to be quite far from individual, like ubiquitous computing, but most of my projects turn out to be like directly connecting those two sides. Okay, think about it, right? Earlier, my driving like the plug-in hybrid electric vehicle, right? You're talking about designing better electric vehicles, but it's about users' behavior, right? How they drive their vehicles, where they drive, like how they use their charging facility, right? And on the other side, right, if you know like how users have different preferences, you can design like, or for example, the air quality side, right, can be actually also designed accordingly so that you can work with like accommodate different user behavior. So all this really kind of like give you a big picture, right, of what I do. So high level things, right? We work with the data, but we really look at like the integrated view, okay, of what the real world problem is. That's actually always the starting point, right? We want to be solving real world problem, but then you want to be able to identify the challenges, right? Because we're still doing scientific research, right? So what is the novelty, right? What are the particular contributions of your work, okay? And also the fact like, because we work with very different domains, right? We do have students like coming from actually different backgrounds, and their dissertation work can actually focus on different aspects of the full stack. Okay, so I have some small slides, right, going into the individual aspects, but I'm going to stop here and check quickly whether we have some questions right now. I'll go back to the previous slide in case people want to ask some questions there. And if not, then I can continue with a lot more, like a few more slides talking about some of the specific work in each of those categories. Okay, I see one hand raised. Sushil?
Hi, thank you for this presentation, ma'am. I wanted to ask, since we are solving multiple problems using like sometimes similar data, or we can solve multiple problems using the single data.
Mm-hmm.
So are we implementing any like multitask learning in it?
Okay. Yes. I can, well, so far we haven't directly used that, but I can imagine there are different scenarios that would benefit from multitask learning. Okay. Um, so yeah, so if the multitask learning, so you can you can like see how it works better. That is good, right? But maybe from my side always is what is the application scenario, right? Like when you see like when you say like the different types of data can be used for different things, right? So maybe grounded with some specific like motivating examples, use cases, right? And then you can talk about it, yeah. So this may be another thing like maybe I'll add, right? So when my students, right, some of them have been focused on more of the algorithm side, some of them more focused on more of the application side, systems, right? But a lot of times, like as I said, like you want to start with like what is the problem setting, right? If you say like when you say multitask learning, this is like this is actually there's a lot of research going on, right? So as I said, like I personally, I'm not a machine learning person. Okay, my research like leverage a lot of machine learning methods, and we do have some kind of innovative work there as well. But we usually don't say, okay, we want to work on like a multitask learning and then try to come up with a better, like say, how to say, methodology development. Rather say we're solving a problem, real world problem, but which may actually benefit from like improved multitask learning approach. Do you see what I mean?
Yes, I got it. Yeah.
Mhm. Yes. Okay. All right. Any other questions? All right. If not, I'll continue. So as I said, like so the next sections, I'm basically looking at like different layers and talk about some of the research work we have done. Okay. So it actually covers a lot of work, right? And actually this is a collaboration with a lot of people. Okay. So I would just try to like highlight, right, the challenges of the specific problems and how like maybe the some of the novelty of those work. But I said like there's a lot of details, so I will not be able to get to all of that. But hopefully this will give you a general sense of the different flavors of the research we do. Okay, so the first one is more on the systems side, right? As I said, on the system side, a lot is about how you get the data. Okay, so there's a lot of sensing type of work. So over the years, we actually have worked with very different types of devices, different sensing capabilities for very different problems. Okay, so here just snapshots, right, showing some of the work we have done. Okay, so this is one for running. This is one for air quality, like sensing. This is more of the wristband to identify gesture. Okay, this is like earlier version of the like smart eyewear system. We also use Wi-Fi for different like tracking different behaviors. Okay, so there's just like a lot could do, right? Because they're just existing sensing capabilities and the new sensing capabilities that you can utilize and you can combine them and use them for very different scenarios. Okay, so with sensing, of course, there are different challenges in different settings. Okay, so one thing we did is about Wi-Fi sensing. Okay, so this is using Wi-Fi signals, right? Our motivating example, this is actually about the air quality sensing. So we're working on a mobile air quality sensing project, and the idea is that okay, of course, you want to say okay, if you say air quality good or bad, you want to know where the user is, right? So especially in the indoor space, how do you identify like which room the user's in? So we were using like Wi-Fi signal, particularly this received signal strength to capture like room level localization. Okay, so we did actually a few different work. The first one is a supervisor model, which requires some labeling. The second one is unsupervised, right? With basically trying to identify those hotspots and then try to link them together. And then later on, we actually did this kind of fully automated floor plan construction because we are able to combine like the different signals in different rooms, but also as a user move, right, between those rooms, then you have a sense of how those rooms are connected and how big they are. Okay. So this is like a very different types of work, but they really showcase like how the system aspect and also the different algorithm design come together to support very interesting real world application scenarios. And later on, we also like continue the Wi-Fi sensing, but now looking at the channel state information. So this actually has been a lot of research on this domain, like using the CSI signals to do actually a lot of things. Okay, so we did quite a bit in terms of like just indoor human tracking, right? So the high level idea is that when objects like subjects are moving, right, in the particularly in the indoor space, right, with the Wi-Fi signals that will be actually changed, right, corresponding to the movement of the objects. Okay, so if you have some way of tracking, right, where the user is moving, then you actually have this kind of from the lower level, just saying, okay, I'm seeing some changes of the signal, and then you can track, right, do the spatial temporal tracking of the user. And also if you couple that with like some kind of living space, then you can also capture like what the user is doing, right? The user is like in the living room, in the bedroom, in the like kitchen. So you actually can capture some very useful information from those kind of sensing. Another very different one, still using the CSI signal. This is actually for Morse code input. Okay, so this is particular for people with like severe, like the muscle, kind of very limited like muscle movement capabilities to the point that they can really just move their finger. But with the finger, like we're basically talking about like up or down, and that's actually kind of translate to the like Morse code, right? The short and long signals. Okay, so we were able to design our system and actually have some very interesting algorithm design work in this kind of very subtle movement, but also kind of fairly kind of noisy, like real world setting. Another one is about boundary detection, because in the Wi-Fi sensing scenario, right? So you want to be able to like use that to again kind of identify the sections, right? Knowing where users are, or for intruder detection, somebody entered, right? A place that they're not supposed to. So using Wi-Fi signals, we are able to actually identify, right? Especially like when the signal goes through a wall, you actually see quite a bit of change. Okay, it's noisy, but we are able to pull out a pretty clear signal, so we can actually differentiate, right, whether a user is inside or outside a particular boundary. Another one, this is some of the more recent research we've been working on. This is about like smart eyewear systems. I don't know how many you have like work with like those kind of head-mounted devices or smart eyewear. What we're looking at is something that is kind of combining, right, two cameras, right? One is a camera looking forward, right, whatever the user is seeing. Another camera is looking inward to see like what the like basically a lot of in terms of eye tracking, because you want to see the user's attention. Okay, so there's actually quite a bit in terms of the system design and also the algorithm design, because particularly you want to be able to take the different types of data, right? Fuse it, but in a kind of like real-time or near real-time fashion, and then doing it very efficiently so that it actually is usable, right, for different purposes. So we had a few different papers on this. The first one is more of the attention, right? So it's like if you want to, because like when you look at the different things, sometimes you're paying attention, sometimes you're not, sometimes you're paying attention to this corner, sometimes you're paying attention to something else, right? So by combining the eye tracking aspect, knowing what the user is paying attention to, and also like knowing what the view, right, is, right? So you actually have some way to efficiently combine the different information, okay? We further actually developed this to go beyond attention. We're actually getting this emotion angle, because when you look at the different things, you may actually have different reactions, right? Emotional reactions. So that actually was very interesting, like which allowed us to actually capture like what may have like correlations with the different emotions of the user. One more work we did, this is actually voted by the like students. This is actually about like now we're actually using this on dogs. Okay, so we're trying to see from the dog's eyes about what the dog may be paying attention to. Okay, so you could say like some of the like same line of research, but the challenge and the focus will be different in this case. But the idea is that now actually for the first time, right, you actually can see from the dog's eyes, right, what dog is paying attention to, right, when their environment or with their owners. Okay. Pausing quickly to see whether there are questions. If not, I'll continue. Okay, all right. So I talk about systems, right? So that's a lot about the sensing, but also still like connecting with upper level algorithm design and application scenarios. The middle layer, a lot is about algorithms, right? So in this case, it's like you have very different types of data. then the focus is about how you fuse them together, okay? So we have done different types of settings, okay? The first one is more about the user, right? Think about a user, you have the mobile, you have the social network, you have whatever content the user interact with, and then the network structure meaning that the interactions, right? Or like when you attend the same event together, right? That's also the kind of information that we can link people and events together, okay? So actually we did this kind of like event based like social network, because you have both in the cyberspace what people interact with, but also in the physical space we then attend the same event. So that actually allowed us to capture, right, users with similar kind of interests, groups with similar group, users attending them. And then that allows us to make recommendations about if you're organizing an event, right? How you can make an event more successful by targeting people who are likely to join and also choosing venues that may be more effective. Another one, this is in kind of more of the scientific discovery settings. It is about ozone. Okay, so some of you may know, right? Ozone like concentration can be bad, right, in many places. Okay, so we want to be able to make predictions about the ozone concentration. Okay, but ozone the concentration is impacted by many different things, right? So this naturally calls for some kind of fusion of very different like types of data. Okay, so you have data that's more of the point based. You have data that's more of the network structure, for them the transportation network, right? And then you also have the land use, because all that impact the behaviors or activities, right, around a certain area, okay? So in this case, we are able to come up with a fusion strategy. In particular, it's group-based, meaning that different attributes may be correlated in different ways. So by putting them into different groups, we actually had a more effective fusion mechanism. Another one, this is about anomaly detection, okay? So anomaly generally, of course, refers to things that are different, right? The challenge with anomaly usually is that you don't know ahead of time, right? Sometimes you can say you can use threshold, right? If it's above or below a certain threshold, yes, it's anomaly. But in many real world settings, those are like contextualized, meaning that anomaly is relative, right, to the current like status or relative to what you may have seen before, right? So we have worked with like remote sensing data, right? In this case here, like quite quick example, if you just look at the visual, you can see there are definitely things changing, right? There are spikes and they're like significant shifting, and then there also this kind of like bigger kind of band of variations, right? So all those are changes, right? To what extent they are anomalies, right? So that's all the things that you want to be able to pull out in an automatic fashion. Okay, this actually also relates to a bit of kind of the data management. Okay, so I'll not go into all the detail, but high level things that in this particular case, we change the way you organize the data so that you can look for temporal changes. Okay, because this one with a particular application is about like this with like Greenland ice sheet. You're looking for those melting water on top of the ice sheet, okay? So the changes can be slow or can be sudden, and those sudden changes are what scientists are looking for, okay? So we were able to like develop this as more like anomaly detection problem setting, so that you can find like gradual changes, but more importantly, how things are changing suddenly, so that you know there's something significant happening. Okay, and this process is much more efficient, right, compared to like what scientists were doing, like when they were just doing really kind of like flipping through those like satellite images to identify changes. Another one we work on, this is about wind and a solar farm. Okay, still, we're talking about anomalies, right? But here's very different, right? Wind farm, solar farm, they generate electricity, okay? And they generate, of course, with very different mechanisms, okay? So the high level thing is that, okay, you are expecting, right, certain type of electricity generation, but that is very dependent on the context, right? The weather may be changing, the wind speed, wind direction, and many other factors, right? So to what extent you can know this is related to maybe like system failure, right? Or even actually prior to the like certain component being like failing, you can identify something ahead of time. Okay, so wind farm, we did that one. We also did actually a bit more with like solar farms. You can see in this case, right? So the solar farm one is also very interesting, right? The one thing we look at that particularly, well, instead of using a general like anomaly detection mechanism, we look at the structure. Like if you look at the solar panels, right? So they actually have a particular way of organizing those like solar panels, right? So you have the PV string and then combiner box. So the general idea is they have this natural hierarchy, okay? And with this kind of hierarchical structure, then you can leverage that information, because the idea is that even though like if you look at a big solar farm, things may be different, right? You may have cloud coverage here, you may have a dust coverage, or there's like high grass, like covering shadow or something. But then if you look at your neighboring panels, right, they're expected to be similar, right? Meaning that if they're all performing normally, then you actually would see similar performance. And that is what we're leveraging to like identify abnormal behavior. Okay. Later on, we actually had another design. So the idea here is that yes, hierarchical structure is good. Looking at your local neighbors are helpful, but that's not sufficient, right? Sometimes you actually look at like maybe another panel that's like on the other side of the solar farm. So they're different in terms of location, and the environment may be different at the same time. But if you look over time, you may be able to find things that may have similar context, right? At a different space and a time durations, okay? So by putting all that together, you actually have more information. So you're looking at both your local neighbors, but also other neighbors that are further away, but may have similar context for you to compare with. Okay, so all those I can see, right? The application is something concrete, right? The data is actually a lot. It's quite interesting to look at the data, but ultimately it's about how you take the problem, right? The data, the application together, but then have some very interesting kind of technical design to make this work more effectively. All right, checking on quickly, no questions yet. Okay, so I'll finish this up. So hopefully we'll have a little bit more time for Q&A at the end. Okay, so the satellite system algorithms, and you probably actually already seen some applications already, right? But application-wise, I feel this is really also why it's so exciting, but also really can make some real-world impact, because we are dealing with real-world problems. Okay, and when you look at those problems, you work closely with the domain experts. They have very different types of data. The kind of questions they're asking is very different, but it is about how we utilize, right, our capabilities, right, from the data analytics side to tackle, right, to tackle very different. Okay, so a few examples. Okay, this one is on earthquake. Okay, so course, I used to think, right? So like earthquake usually is about like warning, right? Or like prediction. No, you cannot predict earthquake. A lot of times it's about detecting it quickly. And so you can send out early warning. Okay. So in this particular setting, it's about how you can leverage mobile phones, because all our mobile phones, right, have some kind of like motion sensing, right? So if your phone is on the table, and if there's is some kind of like earthquake movement, then there will be vibration, and it has a particular signal. Okay, so you can actually use those signals, right, to detect earthquake. The challenge is that those phones are very diverse, right? We have very different brands. They have very different types of sensors, and then like how they're being used can be very different, right? And they're very different coverage at different spatial temporal granularities. Okay, so to pull this all together is that okay, how you take all those kind of weak and noisy signals, right, from all those different devices and aggregate that in a way such that you can have like a high accuracy and also like a very short like response, right? A very quick response when some earthquake happens. Okay, so we did quite a bit of analysis just to look at the very different like signals and then building up the kind of the network-based detection mechanism so that we can detect this in very different settings. Another one, this is about a fish, right? Or they'll talk about earthquake, and now it's like we're going to the ocean. Okay, so the here the scenario is that this is about acoustic signal. Okay, so the like what NOAA, which is the oceanography like side, so they are basically sending out the boats right to the ocean, and they're using some kind of acoustic signal to kind of check right what may be underneath right the water. Okay, and the goal is to find fish schools. Okay, the signal is actually very noisy. Okay, so if you like, this is what the manual annotation process, right, that our domain expert be doing, right? So there's actually many steps, and that takes a lot of domain knowledge to be able to characterize, right? So this blob may be like fish school. Okay, so we're trying to replace it with a new automated framework. Okay, at a high level, what we're trying to do is that we want to detect those blobs. Okay, so really just the things that are kind of maybe potentially representative, right, of some fish school, and then be able to classify what kind of fish school it is, or this may be some other type of like biologic or pattern that we may be looking for. Okay, so we're currently actually ongoing. So we're actually looking at self-supervised learning because they're just very limited label. Okay, we're looking at the decades of data. That's like almost 300 terabytes of data. So we definitely want some way to do this. Okay, so we're looking at both the algorithm itself and also how you can build this as a kind of cyber infrastructure so that this can be utilized like for like the research community, and actually we can quickly like look at a huge amount of data. Another one, so this is the one I kind of mentioned at the very beginning, right? When we're doing this plug-in hybrid electrical vehicle, that was 10 years ago. Okay. But then a few years later, right, we actually like come together and we got this large award. This is from National Science Foundation for Engineering Research Center. Okay. So this is those are huge grants, right? It's like 5 years grant, and then you have a renewal for another 5 year. Okay, so the focus now is much bigger, right? Instead of looking at an individual vehicle or individual like a driver, we're looking at the whole ecosystem. Okay, so we're looking at like say transportation electrification. So it's like you want to actually push out, right, the whole ecosystem. You're looking at like electrifying across very different vehicle classes in very different usage scenarios. Okay, how do you do it? Okay, so starting point, of course, you need to look at your usage scenarios, right? So there are many different types of stakeholders, right? There may be passenger vehicle drivers. You may be taking electrical buses, or like you may taking electric train, or like you may be doing like a work in say airport or like in a farmland. So they're very different usage scenarios. So we want to really work with our stakeholder to understand the very different types of usage scenarios and the preferences, or what kind of technology would be more suitable, right? So then the other one part is about, yes, what kind of charging technology is there? And we're actually developing state of the art, right? Like charging capabilities, both for wired scenarios and wireless. So that means you can have actually in motion charging. This is something I'm learning, right? So you could actually have like the charging cables, right, embedded in the road. So as you're driving through it, right, you can actually charge your vehicle. Okay, so the high level thing is that, okay, there are different technologies, there are different usage scenarios, right? So it really comes to this about a smart management, right? Because from the utility side, right, the power grids, right, they have their way of saying, knowing, okay, how they're generating electricity, when, where, how much, right? But then on the other side is the demand, right? When you need charging, how much you need, where you need them, okay? So it's about coordination, right? So how you actually like connect this together, right? So that you know the demand from the charging side and the supply, okay? And you optimize. So there's both the design time optimization and also runtime optimization, okay? So I'm leading the data side. So we're basically looking at all kinds of data, right? Whatever data that we can leverage to be able to capture, right, or model the different components within this big, like what we call systems, ecosystem, right? So you can actually then model the different components, see how they connect to each other, okay, and then like jointly, right, you can actually have some like optimization strategies, okay. Very briefly also mention, right? So we talk about scientific discovery as like one category of the applications, but a lot is about the people, right? Ubiquitous computing, okay? So I'm not gonna get into detail, but here are just some numbers, right, to drive the motivation, right? Because ultimately, right, think about how many people use mobile devices, right? How many of us are maybe using wearable devices, or how many more like IoT devices are being installed, right, everywhere. So because of that, right, we actually have a lot of data, a lot of capabilities, right? We can do a lot with it. Okay. The other domain is the social networks. Okay. So this is where like you can actually get a lot of information. Okay. You can understand the different like user perspectives. You can also track how people respond to different things. Okay. One other thing I want to highlight is about the cyber safety. Okay. So this really gets to the point about when you go to the cyberspace, yes, great, there's a lot of information. It can be very helpful, but there's also this dark side to it, right? Information may be bad. There may be like users who are malicious to some extent, right? So we want to have this kind of capabilities, right? Through data analysis, through some kind of like system building, so we can actually detect those kind of bad behaviors quickly and hopefully mitigate, right? So as you can see, again, like we're working with some of the data related technologies, but they can really like help or be impactful in the real world. Okay, I'll skip this. This is just like some analysis we have done. For example, like this is using Reddit. We did NBA fan community analysis, which is actually quite interesting. I know a little bit about NBA. Some of you may have more knowledge, but there's actually using this kind of data, you can ask very interesting questions. And we actually found some interesting behaviors about how the fans of different teams respond to different types of like events. Okay, this is about electrical transportation, right? We're using social network trying to understand the public opinions, like how people like think about like whether they're paying attention to electrified transportation, what are their major concerns, which communities are more like either pro or against or focus on particular aspects related to electrified transportation. So all this can be very useful in terms of like understanding like user concerns, user preferences, and also could be useful for policy making going forward. All right, I think I have one more slide. Yeah, so this is about what hopefully this will give you a big picture, right? What I do, okay? Systems, algorithms, and applications. Some of the newer algorithms aspects we're looking at, right? With sensing, it's really about, yeah, you have existing sensing capability, there are new sensing capabilities. How do you build up, right? Like new solutions so that is efficient and also robust in the real world setting. Okay. Algorithm side, a lot is about fusion, right? But knowing that the data have uncertainties, right? Inherent uncertainties, how do you actually capture that as you fuse different data modalities? A lot of that is about contextualized analysis, okay? So anomaly detection, a lot of them is contextualized. How do you actually make that, right, adaptive to the changing environments? Also, application-wise, we're always open to new applications. I feel like there's really still a lot we can do, right? So really it's about the kind of like talking to different people, right? Learning about interesting new problems and see how our research work, research expertise, right, can help in the different setting. Okay, with that, I think I'm done with, oh, I have actually. So this is my overview slides out there. But I do want to put this up. This is usually when I end my slide for people who haven't been to Boulder, or if you are in Boulder but haven't seen this view. Hopefully this give you a good sense of where our university is, right? This of like the football stadium and those areas is all where our campus is. It's a very beautiful campus. It's a very nice area. I love it here. So if you either you're here already or you're considering applying, so this definitely hopefully give you a sense of what it'd be like living in Boulder. All right, with that, I'm ending my presentation. So I'm happy to take some questions. No questions? We have pretty quiet group today. Feel free to chat. Really, like this is like a your chance to ask me questions. Anything. All right. Sushil.
Uh, Thank you again. I wanted to ask like about the earthquake detection.
Okay.
So buildings over here are like mostly like created based on the like earthquake. We can say mitigate the earthquake effects on the buildings, right? So if any heavy vehicle or like train is passing by, it's gonna make some vibrations, right? So
Mhm.
how you gonna detect those vibrations from the like act? Is it a true earthquake or is just a false positive? Or
Right. Right.
something.
Yeah. So at a high level, it's about there are different types of vibrations. The patterns are different. Okay. And
Mm-hmm.
also, we're not looking at just one phone, right? That's also why that's very important, right? Because if it's an earthquake, you probably see it in the larger area, right?
Yes.
So in a way, like so this is actually what we're trying to capture is like you want to have some sense about, okay, so at any time point, you want to have some understanding about how many phones may be in this area, okay?
Mm-hmm.
And then you say, okay, if this is an earthquake, right? One, of course, you need to see certain pattern across those phones, right? But also you need to see those phones or majority of those phones being responding to that. Make sense? Right?
Yes.
So if it's a crane just kind of driving through, yes, you will see some vibration, assuming that vibration is the pattern is similar and may trigger a few phones along the way, right? But it's
Mm-hmm.
unlikely to be able to trigger a much larger
Yeah.
number of like phones in that region. So that's one scenario you could consider. So yeah, there are, of course, like nothing is perfect, right? So you may still
Yeah.
be able to mimic a scenario, but it'll take a lot to mimic that kind of thing. So yeah, in a way, just like you kind of know, understand your problem setting, you see what kind of things may be how to say, what you're looking for, right? And then trying to differentiate. So your model would somehow leverage the different types of information, but build in this knowledge, right? That like what you're looking for is like how that can be different from maybe other things, right?
Yes.
Mm-hmm.
I have another question on the sensing using Wi-Fi.
Okay.
So over there you have shown the like corridor structure. Yeah.
This one?
Yeah. So
Okay.
over here my question is there are some part of building which are like unused, or like most of the people don't use it just because it's little inconvenient, or
Mm-hmm.
say like it's not pretty used. So how
Okay.
solve it, because it will create a what we can say imbalance in the data, right?
Yes. So that's actually a very good question. So there are potentially, well, there are a few. Okay, I'll list maybe a few scenarios for this. One, if it's about air quality, you care more about when there's people around.
Mm-hmm.
Right? So if there's like one section that's just like people don't go there or very few people go there, that means yeah, in our system design, we just don't get enough data to be able to map out that area, right?
Mm-hmm.
So yes, so we're missing on that area, but in to some extent that's okay for our application scenario because if nobody's there, I don't care about the air quality. Does it make sense?
Yes, it does.
Right. So that's one side, right? Another one is that you could say, okay, maybe my scenario is that I do want to actually have a full map. Okay.
Mm-hmm.
For different purposes. So in this case, then you can consider the different strategies, right? Either like, of course, crowd sensing is a broader use. So if there's a scenario that you see the need, you actually can have a campaign, you actually pay people or motivate people to go to explore the different areas, right?
Mm-hmm.
Or like, for example, in the kind of like fire rescue or rescue or like rescue or like some kind of emergency scenarios, you actually have like a robotic mechanisms, right? So they may go in explore. So as like even if it's not people, you have some way of getting to those areas and then leveraging the Wi-Fi signal, then you can augment what you already have with those kind of information. But that again depends on your application scenario, right?
Mm-hmm. Yeah.
Yeah. But this is a good question. But as you can see, right, all of those you need to kind of connect to your application intended application scenarios, and then you may have different strategies from your technical side, right? How you can get the data you need and build up the information, the model you need.
Yes.
Mm-hmm.
And another one is automated the data from the vehicles, uh,
Uh, what
starting
do you,
slides, like starting slides below 10.
the hybrid. Yeah.
Yes.
This
Yes.
one? Yes.
Yes. So it's kind of I have worked on some work, this kind of data, vehicle for everything.
Okay.
Yeah. So it gives you
V4 or
information.
V2X.
Yeah, V2X data.
Okay. Mm-hmm.
So it gives you information like how people are driving, how people are responding towards their abnormal behaviors, like sudden braking, taking sudden
Mm-hmm.
turn, and everything. So how you detect the yes, it's very less in terms of it's imbalanced data.
Mm,
People don't normally rash drive or everything, but
mm,
how you implement, how you can take information from it, since it's a less small data. in terms of like battery usage and vehicle like battery capacity and everything.
Mm-hmm, mm-hmm. Um, yeah, that's how let's say. So V2X has been around for quite some time, and there have been quite some effort, right, trying to like deploy like the infrastructure collecting data. So we're actually looking at a few of those data sets. Um, as you're saying, right, it's challenging because they don't have perfect coverage, right? Actually, there are a lot of issues in those kind of data sets, right? So in a way, just more like you need to see what is available, right? And then what is feasible, right? So if you talk about like, yeah, driving behavior, right? So if this like dangerous or risky driving behavior, again,
Mm-hmm.
you're asking the question, what you can see, right? From the V2X side, right, what you can aggregate, one from the per vehicle perspective, what you can get from more of the kind of the roadside unit or like from the kind of, you may have some kind of server that's monitoring the area, right? So it depends on how much information you can get. Okay. Um,
Mm-hmm.
we're actually doing something kind of related, maybe not exactly what we're looking for, but we're looking for some kind of general just misbehavior, like information. The idea is that we're using V2X, but particularly we're using the this is like a basic safety message, right? BSM, and then we're just seeing like whether there are patterns that just look very different, right, in a spatial temporal setting. Okay.
Mm-hmm.
So yeah, there are actually a few angles to it, right? One, we also realize there's very limited data, so we actually are working on some kind of like data generation process, so that we can actually generate the data of different scenarios. That's one. But also, then you're basically trying to capture how much information and how much confidence, right?
Mm-hmm.
Because it's about your data coverage and the uncertainty angle, right? Because depending on how much data you have and also what kind of behavior you're looking for, you may or may not have enough kind of fidelity in terms of whether this is like say a bad behavior or just like you don't have enough information or your data is noisy. Right. So this is a definitely very interesting angle. We're still in the middle of it, so I don't have the full solution yet. But I think, yeah, at a high level, it is about how much information you can capture, how much of the pattern you can model, how much you can augment your data, and also some kind of uncertainty measure you can tie to different scenarios. Does it make sense?
Yes, it does. I was
Mhm.
thinking about it because it's a less data that we have, and we have to train our model on that less data. So, but
Yes. Yeah.
it will influence on the real data that people don't normally rash drive, but model might be predicting it that they're doing it.
Mm-hmm. Mm-hmm. Yes. Yeah. Yeah. So there are, I think this is actually very like there are different flavors of research going on. The set like getting more data, augmenting your data, right? And also be able to maybe focus on specific scenarios instead of looking at the broader, like a wider set of cases, right? And others should give you like at least some improvement in terms of how much you can do. Not sure whether that's good enough, but at least you can make some progress by kind of focus on some of those aspects.
Yeah, true.
Mhm.
Thank you.
Yeah, sure. All right. Any other questions? Well, actually, Megan, like I know are we still recording, or maybe we can stop recording so people can ask questions more freely.
Sure, I'll stop it now.
Yeah. Okay. Yeah. So we're